You learn much about the world around you through sounds. You can communicate with other people through speech, and medical diagnoses are often done through ultrasound waves. And most animals communicate with each other through sound.
Sometimes, animals are to detect the presence of their enemies, even at far distance by the sound their enemies produce. Cats can easily pinpoint a mouse's location because the structure of their ears enables them to listen in all directions without moving their heads. Sound waves are produced by longitudinal vibrations of molecules in gases and other media. This means that as a wave travels through a medium, the molecules of a medium oscillate to and fro. The energy of this vibration is carried by the involved waves, which is brought to our brains for interpretation. Sound waves that travel in air come in contact our eardrums, causing it to vibrate. The capacity of matter to transmit sound depends on its elasticity. Elastic solid transmit sound well. Inelastic ones like cloth, rubber, plastic, and sponge transmit sound poorly. Liquids in general are better conductors of sound than gases. If two hard objects are struck together underwater, the sound heard by a person that is also underwater is louder than when heard with air as the conductor through which sound travels.
Why is liquid a better transmitter than gas? And why is solid considered as the best sound transmitter? You know that particles in liquid are closer to each other than the particles in gases. So sound waves are transmitted faster and more efficiently in liquids. Between liquids and solids, the particles of solids are even closer than in liquids. Therefore, sounds are more easily and efficiently transmitted in solids than in liquids.
Thunder is heard a few seconds after the flash of the lightning is seen. Similarly, an observer standing at a distance from a gun will see the flash of light before hearing the sound of the gunshot. This shows that sound travels slower than light. The velocity of sound varies in different media. It depends on the elasticity and density of the medium. In general, the more elastic the medium, the faster the sound can travel. The sound can travel faster in a solid medium than in liquid or gas because the elasticity of solid is greater than that of liquid and gases. The table on the left shows the velocity of sound in various media. These values depend on temperature. It has been found that the change in velocity due to a change in temperature is more significant in gases. In air, the velocity of sound increases approximately 0.60 meters per second for every 1 degree Celsius increase in temperature. The speed of sound in ideal gases is represented by the equation V sub sound in ideal gases is equal to the square root of gamma RT all over m, where gamma is a constant which is related to the nature of the gas, which is 1.67 for monoatomic gases and 1.4 for diatomic gases. R stands for the universal gas constant, having the value of 8.314 joule per mole Kelvin. M is the molecular mass of gas in kilogram per mole. T is temperature in Kelvin. Now for ordinary air, we have V sub in air is equal to 331 plus 0.60 T sub C meters per second, where T sub C is the temperature in Celsius. For liquids, the velocity of the sound is given by V is equal to the square root of beta all over rho, where beta stands for the Mach modulus of the medium and rho stands for the density of the liquid. And now for sound waves in solid bars like rods, the velocity of sound is given by the equation V is equal to the square root of y all over rho, where y stands for the Young's modulus of the medium and rho is the density of the rod. So let's have an example. Compute the speed of sound in helium gas at 700 degrees Celsius. We have givens like the temperature, which is equal to 700 degrees Celsius, Another is a universal gas constant, which is equal to 8.31 joule per mole Kelvin. The molar mass of helium is equal to 4 grams per mole. And since helium is a monatomic gas, we assign a value of 1.67 to it. And to solve for it, we have to use the equation V sub sound is equal to the square root of gamma RT all over M. Placing their values, we have the square root of 1.67 multiplied to 8.31 joule per mole Kelvin multiplied to 973 Kelvin all over 4 times 10 raised to negative 3 kilograms mole. As we may notice, we converted 4 grams into 4 times 10 raised to negative 3 kilograms to cancel out units. Solving for it, we will have an answer 1,837 meters per second. Rounding up, we will have the sound velocity, which is equal to 2,000 meters per second, or we can express this into scientific notation and write it as 2 times 10 raised to positive 3 meters per second. Example number 2. Show that the Mach modulus of water is 2.1 times 10 raised to positive 9 newtons per meter if the speed of sound is 1,450 meters per second. Sound velocity is given at 1,450 meters per second. And then we are asked to find beta sub water, or the Mach modulus of water. To solve for it, we have to use the equation V is equals to the square root of beta all over rho. And since we are looking for the value of beta here, we can write this equation into V squared is equal to the beta all over rho. Then therefore, beta is equal to V squared multiplied by the rho. Placing their values, we have the sound velocity, which is equal to 1,400 meters per second, squaring it and multiplying it by the density of the water, which is equal to 1.0 times 10 raised to positive 3 kilograms per cubic meter. We will have a final answer, which is equal to 2.1025 times 10 raised to positive 9 newtons per square meter. Intensity and loudness. When the bell rings and you ask someone how intense the sound produced is, the person will most likely to answer you according to how loud it sounded. Usually, a very loud sound is described as very intense. This is a qualitative way of describing sound on the part of the listener. The quantitative description of the intensity of sound is determined by a sound level scale called Decibel Scale. Sound intensity is the amount of sound energy flowing each second through a unit area perpendicular to the direction of propagation. Note that E all over T, or energy all over time, is power. Then sound intensity may be expressed as power per unit area. It is expressed in terms of watts per square meters, and in symbol we have this. I is equals to E all over T multiplied by 1 all over A, or simply we can write intensity is equal to P all over A. The table above shows the intensity of sound at different sound levels in decibels. The defining equation for the decibel sound intensity level, in symbols we have L sub S, is L sub S is equal to 10 log I over I initial is equal to 10 multiplied by the quantity of log I minus log I initial, where I stands for the sound intensity and I initial is a reference sound intensity equal to 1 times 10 raised to negative 12 watt per square meter. Further derivation will lead to the expression L sub S is equal to 10 multiplied by log I plus 120. Example, what is the intensity level of the noise created by children playing in the playground? The sound intensity of the noise is 10 to the negative 5 watt per square meter. To solve for it, we have L sub S is equal to 10 multiplied by the quantity of log I minus log I initial, where log I initial is equal to 1 times 10 raised to negative 12. L sub S is equal to 10 multiplied by the quantity of log 1 times 10 raised to negative 5 minus log 1 times 10 raised to negative 12 will give us 10 multiplied by the quantity of log 10 to the negative 5 minus log 10 to the negative 12, or 10 multiplied by the quantity of negative 5 minus negative 12 or 10 multiplied by 7 is equal to 70 decibels.
A sound wave is reflected when it strikes another body, such as buildings, cliffs, or wooded hillside, and the reflected wave is called an echo.
The reflected surface must have to be at least 17 meters away from the source in order for the echo to be distinct from the original sound. If the reflected surface is less than 70 meters, the reflected sound wave just blends with and strengthens the original sound. A repeated or multiple echo may be created if the sound wave strikes parallel reflecting surface at different distances, as in the case of the roll of thunder, which results from the reflection of the sound from succession of mountains. Like all other types of waves, sound also undergoes refraction when a change in medium takes place. One of our previous equations indicates that the velocity of the sound in air changes as the temperature varies.
On a clear sunny day, the Earth's surface is hot. This causes the temperature of the air just above the surface of the Earth to rise, and the temperature of the lower layer of the air is higher than the layer above. Hence, sound should be traveling faster near the surface of the Earth. This difference in the speed causes the refraction of sound waves away from the surface.
On the other hand, on a clear night, the layer of air near the Earth's surface gets cooled faster. Hence, the lower layer of air is colder. As a result, sound travels faster at the higher lower than the lower layer and is refracted towards the Earth's surface. The speed of air is different at various levels above the ground. The speed of sound in air near the ground is increased if the air is moving in the same direction as the sound.
Can the ear detect all forms of sound waves? The human ear can only detect sound waves with frequencies in the range of 20 to 20,000 Hz, and this is called the audible range. This range varies from one individual to another, but in general, as the person grows older, the highest frequency limit is reduced to only 10,000 Hz or less.
Sound waves of frequencies above 20,000 Hz is called ultrasonic waves. These waves also reach the human ear but are not detected. They can be detected by some animals. Dogs can hear sounds as high as 50,000 Hz. Pool bats can hear as high as 100,000 Hz. Ultrasonic waves in the field of medicine are used to probe human internal organ instead of X-rays. Sound waves with frequencies below 20 Hz are called infrasonic waves. Common sources of these waves are vibrating heavy machines, earthquakes, thunder, and volcanoes. These waves are inaudible but can cause damage to the human body. Thank you very much for watching. We hope that you learned. See you on our next topic. Bye!